Okay, everybody. Sorry that I'm starting streaming about a minute or so late here. Um, let's see. Let's take a moment to gather everything together. Let everybody um, look through, or we look through these notes while I wait for folks to come on in. Let's give it about a minute or two here. Maybe just a minute. Okay, I think we have all of our usual attendees here tonight. So it's a good time to get going on the lecture and take this Monday into the math zone. So if you recall, last time we were in section what or we were working through section 1.3, some elementary functions, and we were just talking about sine and cosine, these good old-fashioned trig functions that we all know and love. So we started by building out the exponential function. Then we built sine and cosine. Accordingly, I'm going to kind of really quick go through here and make sure that these are super visible. But we built sine and cosine accordingly just through these power series representations. And if you recall, this is all just purely heuristic at this point. So we haven't genuinely shown that these power series converge or talked about what convergence means in the complex plane. So right now, these are heuristic notions, these arguments involving convergence. We'll show later that they hold in a rigorous sense, but we're basically just defining a function that we're going to call e to the z, the exponential function. We're just going to call it that. It happens to agree with the real exponential function when you restrict z to the real axis in c. But whether it's the right thing in some moral sense to choose, not really clear. Maybe you could pick something else. We don't have the true justification to say that the power series type arguments really hold, any weight. But we'll get there. So we used these power series arguments. We got a workable definition for sine and cosine, which I've got here up on the screen, defined in terms of this first thing that we've built up, e to the z, and so on. Built these guys. And so what we're going to do now in the remainder of this section is we're going to build a bunch of other functions in similar ways and show that, or not a huge amount, just a number of other functions in similar ways, and show that the general properties that you expect to hold from the reals can carry over into the complex situation. So, for example, proposition 1.3.4 in your textbook shows that the complex valued sine and cosine continue to obey a lot of the identities that we all know and love from classic real numbered, real valued sine and cosine. For example, their squares sum to 1. Sine squared z plus cosine squared z is 1. This just says that, you're still sitting unit circle stuff, right? All right, fair enough. You've got nice identities like the sine of a sum is sine of the first piece of the sum times cosine of the second piece plus cosine of the first piece times sine of the second piece. That is, you switch the sines and the cosines, right? And then if you do the cosine of a sum, you do cosine first piece, cosine second piece, minus sine first piece, sine second piece, right? These classic double angle type, or sum identities from trigonometry, and these guys still carry over. A number of other things along this line can be proved. Here's just a couple of them. Nothing amazingly special in these proofs. It just is a routine application of the definitions given up here. So you just want to go through and actually show that these things do hold. Basic algebraic manipulation. Nothing remotely interesting there. Of course, we can use these two guys to define all the rest of the regular ones, tangent, cotangent, secant, cosecant, so on and so forth, right? Whatever the other variants you'd like to see, there's kind of a lot of different trigonometric functions beyond these guys if you want to get into weird trig world, which sometimes people do with complex. We're going to skip over anything like that. Just the regular trig functions work the same way. You just define them in terms of these guys, and these guys are defined in terms of these e to the z pieces and so on. And bada boom. Nice. Now we can, we will face a more interesting challenge in defining the logarithm. The logarithm will be the first thing that presents us a genuinely interesting difficulty. Or maybe not a difficulty so much, but certainly a little bit more nuanced than what we've touched on so far. So in particular, what we're going to have to deal with is the periodicity of the complex exponential. That is, if you'll recall, I want to pull this over in exactly the same way I wrote it last time. Okay, yeah, there we go. That's how I wrote it. So if you'll recall, e to the z we defined as being given in the complex world as e to the, now I'm going to just write this all in terms of z instead of using x's and y's. It's e to the regular old real exponential, real part of z times cosine mz plus I sine mz, imaginary part of z. So this was the definition we gave for the complex exponential function. We had this nice little thing right here. We might have written it in terms of x's and y's before, but writing it all in terms of z, it's like this. Notice that since cosine and sine are indeed periodic, just to remind everybody, obviously, we get that the exponential function here is also periodic. Namely, recall that in the complex world, periodic just means a function f of z is periodic if there exists some w such that f of z plus w is f of z for all z, and w is called a period. So this is periodic in the complex world. Okay, yeah, fair enough. All right. So the challenge that we come across with dealing with the logarithm, and this would be the same kind of challenge we'll come across with all of the inverse trigonometric functions in the complex plane and so on, is that we're essentially trying to we no longer have as nice of behavior. It's really not any different than like the problems we encounter in the real case for dealing with like inverse of, say, like a tangent or something to that effect. But it is a little bit more, it does require more nuance than how we've been able to proceed thus far, just making use of one kind of a power series intuition argument. So, and here's the basis, the building blocks for how we're going to start to look at this. So we're going to let a sub y naught denote the set of complex numbers x plus iy, with y, the imaginary part of the complex number, between y naught and y naught plus 2 pi. So it'll be a 2 pi thick strip, not including the top part, starting at y naught in the imaginary axis. So just basically right up like that. Now, this is where everything, where one probably has to remember a little bit of notation, particularly if you don't, or terminology. If you don't remember what one-to-one and onto mean, just remember that one-to-one, and I won't draw all the pictures here that I like to draw in calculus classes or linear algebra classes if you've taken any of them with me. One-to-one just means that every output is uniquely produced by a specific input, and onto means that you get everything in the codomain as an output. That is, I'll write it like this. A function from a set x to a set y is onto if f of x is y. That is, the image of x under f is just the entire set y. And it's one-to-one if f of, and I should maybe make these capital X's and Y's. I'll do it like this to make it super clear that I'm describing these as sets. As if f of little x equals y, we'll maybe say little x1 or something like that, and f of x2 equals y, then x1 equals x2. So this piece right here, so this first part implies the second part. This is 1 to 1, or injectivity. This piece right here is onto, or surjectivity. So when you have 1-to-1 and onto, then you have a bijection, as it's called. And this is what is necessary to invert things. That is, everything gets hit, and if it gets hit by a unique thing, right? Everything in the codomain is mapped to by something in the domain. And if it's mapped to by something, well, that's the only thing that gets you there. All right, so I'm going to erase that really quick, save ourselves a little bit of space. But just a really quick diversion, so this last part of this doesn't mean nothing if you've forgotten that. So this set, the complex numbers x plus iy, where x is any real number, any real part, and y is between y naught and 2 pi above that, e to z maps these strips in a one-to-one manner onto the set of complex numbers other than 0. And if we want to actually see this, I'm going to have to go back and I'm going to erase a few things just to make our lives a little easier. If you want to actually see what this looks like, here's the picture to envision. This is it. You've got this strip. This is something, this is a y naught, as we were calling it. It's a strip from y naught up to y naught plus 2 pi, not including that top piece, right? And z, this notation right here, z, then this weird arrow with a bar at the end of it is called maps to. Z maps to e to the z, this function defined by this action, right? This function right there is the exponential function. And what it does is it gets everything except for 0, that tiny hole right there. So strips like this, it goes over. And notice there's nothing special about y naught. We're not specifying some very particular y naught and saying this is true. We could take this whole thing and translate it down just a little bit even, right? We could just start like right here and just go instead up to partway through. And this strip here will also get mapped over in a slightly different way perhaps. But there you go, right? Okay, so this is what's going on with e to the z. It's taking strips and it's stretching them out into the entire punctured plane right there, basically. It's taking strips without the top part, and it's putting it to the entire complex plane without that little hole right there. So basically the hole up top basically becomes this little hole right here in some sort of a sense. And this is the one-to-one and onto function, e to the z, from ay naught to c set minus 0. And so we should be clear, and I always kind of dislike when people say this because it makes it harder to understand. E to the z as a one-to-one function onto this, it one-to-one and onto requires specifying the domain and codomain, right? Because it is entirely possible to have e to the z specify a function that is not one-to-one, right? What they're trying to say right here is that e to the z is, there exists a function that agrees with e to the z on the domain a sub y naught that is one-to-one and onto if its codomain is the complex numbers without 0. There are as many functions like this as there are y naughts. Nice. And this is a minor distinction, but in case that's not clear, we're not saying that e to the z is one-to-one and onto. We're saying that e to the z restricted to the domain a sub y naught induces a one-to-one and onto function if we take its codomain to be c without the origin. All right, fair enough. So this is what we're going to need to define the complex logarithm, since the complex logarithm should undo the complex exponential function, right? And so this is what we're going to have to start with. We're going to have to take c set minus 0, this punctured plane, and we're going to have to pop it on over to c, and the range, the image here should basically be the opposite of this picture, right? So it'll go back over to C, but we'll just get into this little strip. And yeah. All right. So we're going to send everything over here on over there. And how do we do it? Well, we'll define the complex logarithm of z to be the regular old logarithm of the modulus of z plus I times the argument of z, where arg takes values in the interval, and I don't like how they use this piece right here. Instead of doing the oppositely opened bracket, I think you're probably more familiar with using a half-open interval with a parenthesis. This is a closed bracket, i.e. it's this picture with the bottom line but the dashed top line. So argz will take values in this interval. Remember, we talked about this before, and this maybe is some slight abuse of notation. Maybe we should call this arg sub y naught. But basically, since we can decide arg to take values in some 2 pi thick interval, that is how we will specify the branches of the complex logarithm. And this ends up working very, very nicely. This is still, once again, just a definition. Now, the thing that we'll want to show, and that indeed does end up being the case, is that the logarithm works the way we want it to. This thing we've defined right here actually works the way that we hope it does. And this turns out to be the case. So this is proposition 1.37 in your text. The logarithm is the inverse of the exponential function, e to the z, in the following sense. For any branch you choose of log z, which just corresponds to choosing a y naught, then e to the log z is just z. Oh, okay. And if you choose the branch lying in this little piece right here, from y naught up to 2 pi, right? I mean, you're always choosing a branch like this, right? For some choice of y naught, then the log of e to the z is z for z belonging to that strip. So e to the log z is z for all of the z's except for 0, because obviously you can't plug 0 into the natural log. And then whenever e to the z is taking inputs that are in the right place, that is between, you know, sitting in this in the corresponding strip, then the corresponding branch of the natural logarithm satisfies the property that log composed with e of z is z. Does that make some sense? It works the way we want it to on an appropriate restriction for each choice of a branch. And it also has some of the other nice properties that we're used to. So for example, if z1 and z2 are non-zero complex numbers, then the logarithm of a product is the sum of the logarithms. And once again, this is up to the addition of integral multiples of 2 pi I. And we should be careful here. This just comes from, grabbing a different color, this I arg z right here, right? Namely, you'll have to essentially take this piece, I want to say like mod 2 pi basically, right? Like if you're adding and it takes you out of this interval, right, then we're going to have to put it back to where it should be, right? Does that make sense? So it'll have to stay in here. But yeah, so that aside, it basically says that the properties of logs you want carry over as long as you're careful to loop back around when you're talking about the angle, right, and not go outside of your arg range, if that makes sense. You'll get a lot better sense for it as you start to work with these guys. So, and this is just going to kind of follow. I know I'm kind of booking through this. If you have any questions, please, please, please email me. I will answer all of them. But since there are kind of a lot of functions we've gotten used to using, we're going to have to kind of go a little quick through a few of these guys if we want to make it through this chapter in any reasonable amount of time. So we've talked about the logarithm now, and this is where, pardon one second here, let me make sure I have, here we go. And this is, we've talked about the logarithm, and this is where we're going to do essentially the same trick we did up here with sines and cosines. We're defining them in terms of the exponential to define exponentiation. So we got the logarithm, and ultimately what we want is we want to be able to say things like a to the b in complex numbers or something. Where, let me make this a little bit clearer looking, a to the b, it's a horrible a. So what we're going to do is we're going to define this as, well, here, I'll write it down here so I can write it big. A to the b is, and you might remember this trick from Calc 1. We did this sort of thing when we were doing the derivatives of, say, like x to the x, right? We're going to do e to the b log a. And, oh, I should have said this perhaps. I'm assuming everyone immediately understood. Your textbook likes to use log to mean natural log. Some people do this. Some people like to write ln. We'll write log here. You could write ln if you want. I don't personally care. Use whatever you like. Whatever is best. Your textbook also does the strange and unfortunately antiquated practice of using the reversed bracket instead of a rounded parenthesis to mean not including that side. So I'll probably correct that with my pen because I don't like that. But we do this trick right here in Calc 1. Remember when we were like, oh, we have to find the derivative of x to the x, and so we rewrote this as e to the x natural log x, right? And then we were able to deal with this with the chain rule and a product rule, right? Okay, so we've used this trick before, and it's essentially all we need to do. So we'll define it as e to the b log a, and we'll implicitly understand that this means relative to some choice of branch for the natural logarithm. And this is done by specifying what values the arg function takes on, where we're considering our angle to lie. So this is all we're doing here. We're just going to use this dirty little trick that always works when you're dealing with real numbers, and we're going to say, hey, if it works for real numbers, shouldn't it work for complex numbers? And this will give us the intuition to define our complex analog of exponentiation. And this will let us do a large number of very nice and kind of non-intuitive calculations. So I bet that while maybe you have some sense of what should happen, say, with the squaring function, f of z is z squared, you can think about this geometrically and say things to yourself like, okay, when I multiply two complex numbers, I add the angles and I multiply the lengths. So squaring just squares the length and doubles the angle. Oh, okay, I can picture that in my head. But I bet almost no one has any intuition, intuitively, just intrinsically, off the top of your head, for what should happen when you deal with the function that takes a complex number and raises it to the power of the negative square root of I, right? And that's where this all starts to get a little bit more fun, and why this is a useful trick. So this is a good little proposition right here, albeit it's pretty wordy. We'll talk about this one just for a moment because it's not always that clear what I want to be specific about what's going on here, because this is a nice connection to roots of unity. So if we take a and b, some complex numbers with a not equal to 0, then a to the b is single valued. That is, it doesn't depend on the choice of the branch of log, if and only if this is equivalent to b being an integer. So that means that if you have an unambiguous choice for z to take some complex number and raise it to the power b, you have an unambiguous choice. You have no ambiguity as to what the answer should be, only if that b is a positive or negative whole number or 0. Now, if b is a real rational number, if b is a rational number, p over q in lowest terms, in other words, p and q have no common factors, they're coprime, then a to the b has exactly q distinct values, namely the q roots of a to the p. So anyone here who maybe in their lives has happened to stumble into talking about finite fields or things of that nature, this may ring some bells if you're interested in Galois groups or Galois theory. This will probably certainly ring some bells, and you can start to see the connections between abstract algebraic concepts and some complex analytic ones. If you haven't taken any of those things, if you don't see any connections, then don't worry, we don't have nearly enough time to talk about any of the other stuff that would be necessary to make them clear. But if you've got a rational number of the form p over q, that is just a fraction in lowest terms, reduce it as much as you can, cancel out whatever you need to, then a to the b has exactly q distinct values. And so these are the q roots of a to the p. So this is basically just saying if you take a to the p over q, then this is the same as saying a to the p to the 1 over q. And what we're saying is that this coincides with exactly what you would expect. It's the qth roots of a to the p, right? So we're saying that our exponentiation here is working the way we want. So this thing is going to give you the same answers as when we computed the qth roots and so on. So that's all this entire first part is saying. The next part is more interesting. The next part is weird. If b is real and irrational, or if b has a non-zero imaginary part, that is, if b is genuinely complex and not just like a real number, if it has something other than 0 by that I, then a to the b has infinitely many values. Ooh, now that is pretty wild. You have to choose not only from, say, well, I mean, you could have one thing. You could have some finite number of things, like the q roots of a to the p. And then it gets weirder, and you have potentially infinitely many choices. And this isn't that wild. It kind of comes down to things like, the choice of our branch for arg or for log. And this really is saying that when a to the b has distinct values, these values will all differ by factors of the form 2 pi n bi. So this once again just means integer multiples of 2 pi, right? Just like we're seeing right here, just move over by a 2 pi, move over by 2 pi's, move over by 3 2 pi's, and so on and so on and so on. And since where this is happening is up in the imaginary domain, of course, we're going to have this I factor in there. All right. And of course, this, just like we just hinted at right here, allows you to define nth roots in the way you probably want to. Oops, let me make everything. I think I jumped actually accidentally ahead. I revealed something I didn't mean to. This allows you to identify nth roots just using this complex exponentiation. So the nth root of z, that is z to the 1 over n, in exactly the same kind of way that we did this back in the case of real numbers. We'll define that using this trick, just with e to the log of z divided by n. All right. And this, once again, will be relative to a specific choice of a branch of log z. This is relative to each branch of the nth root function. Okay, so no big confusing things going on here. We're just doing the same trick over and over. We're defining one function, basically e to the z, the exponential map. We're building a bunch of other things out of it. Then we just said, okay, well, we want to invert it, or at least have an inverse that is defined relative to each of its periodic strips, and then we'll build other things out of that inverse that we've defined. So this gives us most of the intuition for all of our regular old elementary functions that we know and love from dealing with real numbers in the complex plane. So this, of course, this root function works pretty much the same way you would expect. The nth root of z is defined so that you can take it to the nth power and get z. So this looks so obvious that the nth root of z to the n is z that you might go, oh, okay. But it is something that you actually have to check. And it's not weird that you have to deal with this, but it's not weird like the proof or anything like that. It's not difficult to show. It's not weird that you have to prove it. It's just something that is worth verifying, and proposition 1.3.12 verifies that that is the case. So among other things, though, it also gives us a formula. So if z is r e to the I theta, then the nth root of z is, and this is just using this polar representation involving the exponential for a complex number. Remember, every complex number can be written in this form. Well, it'll just be the nth root of z written in this form is just the regular old real nth root of r, which is, remember, always greater than or equal to 0 since it's the radius. And then you just divide that theta by n. And this is relative to having theta chosen to lie within a particular interval corresponding to your choice of branch. That is, you're adding multiples of 2 pi to theta, and you run through the nth roots of z, and that's that. So if you want to kind of get a sense of what's going on, there are lots of wonderful animations of this. Let me pull this one up. I had one up. I think I must have exited out of it. There we are. I guess this will do. All right, so I'm pulling up a picture here, and all I'm trying to point out. Oh, yep, there we go. This is what you get if you're graphing the complex log, essentially. When you're choosing a branch, what you're running around zero again and again and again. This is a concept. If you get further along, you might hear about monodromy. But as we run around zero again and again, the question is, when do we cut it so we don't overlap more than once? And you can see this pretty nicely with pictures like, I've got a good little picture here. There we are. Here we are. So yeah, this is the same kind of picture, multiple branches, and we'll just grab one branch. That is, if we cut, we don't want to overlap. You know, if you're looking straight down on it, you don't want to miss, cover something more than once, right? And this is what the branch choices are. Naturally, of course, you could shift this cut point like a little tiny bit to the right or to the left, and then shift the other cut point a little bit right or to the left. This is what the branch choices are. It's just like you've got these kind of corkscrews or spiral sort of things, things that run around points a lot of times, and then you have to deal with this. So you can get some very fun and very complicated. Here, let me see. Let me just give you some dumb pictures. You can get some very complicated looking things if you are dealing with certain less nice things. And these are all these pretty pictures you might see occasionally, but this is not anything too fancy. We're just saying like, hey, imagine running around a circle, right? As you go around it, then you're going to eventually get back to where you started. And if you imagine just continually doing this and kind of stretching that out in time, it's not strange at all that you would get some kind of like a spiraling corkscrew thing, right? Like a spring, And so that's all we're doing. Since we're just choosing arg, basically, how we want to define arg, then that's exactly what's going on here. Nothing super strange or weird. We're just deciding when to start and when to stop in terms of going around a circle. All right. So these are the big main chunks of this chapter, and we're getting near to the end, so I want to make sure I hit everything we wanted to talk about. But the thing to think about here is not, don't memorize every single property. The thing to take home is that the familiar properties of real functions that you are used to, that you've worked with your entire mathematical career, carry over into the complex plane with some minor caveats. For example, the exponential function is no longer, the exponential function is now periodic. That is a big difference from the real case. You also don't have, of course, with this periodicity, you don't have nearly as easy of a way to decide what natural logarithm should be. And we're going to use the exponential function and natural log to build all of the other familiar functions. So of course these ambiguities carry over a little bit further. And they're not bad. It just means that you're saying, hey, this all works out relative to you first deciding something that you could really kind of choose however you want. And that's the whole business of the elementary functions. So I really highly recommend. I know this is a super long chapter in your textbook relative to everything else. I just really highly recommend going and looking at it and making sure that you fully understand these functions. Otherwise, you will have a difficult time. So there's a lot of different examples we could do. Let's start out with something simple. Let's all right, let's do a few of them really quick. So let's find all values of I to the I. So all we're going to do is we're just going to proceed with the definition. So I to the I is e to the I log I. Well, we just continue. That's e to the I, and what is log? Well, this will be, and I should write this right here. I, remember this is going to be 0 plus 1i, right, if you wanted to write it like that. So this will be the regular old log of 1 plus I pi over 2 plus 2 pi n I. Or if you wanted to just take it, you could just you could just pull that I out of both of them and put it together and say, hey, pi over 2, right? That's where I is. It's the arg, the regular old arg. Or we could go for integer multiples of 2 pi past that, right? And this will do us there. And if we start to actually go through and do this, we can do a little bit of simplification if we want. E to the, I should go e to the I, e to the, what's the log of 1? It's 0, right? So this will be pi over 2 plus 2 pi ni, right? And we just go on through here, and sorry if I'm being a little bit slow. Sorry, I had a little bit of something in my throat. We can reduce from here. You can go simplify beyond this. I won't spend any extra time just talking about algebra right now. But notice we've got everything in ways that we can deal with it. Namely, we can simplify this e to the I right now, and this is what I should have done right there. And make sure that everything works out the way we want it to. Go in your book. I don't want to spend any more time right here. And look this up. You'll get down to minus 2 pi n plus 1 over 4. There we go. And nice. Good enough. And all of these values of n are just integers. Remember, integers is 0, 1, -1, 2, -2, so on and so on, right? And so you can just always write n in z. Z denotes the integers. If you want to skip writing the n equals plus or minus 1, 0, plus or minus 2, so on, that kind of thing. Just write n and z, much quicker. I am realizing that I don't think I have enough time to do these examples at the level of clarity I would like to here. We'll start out next time with an example or two really quick. There also are a ton of great examples in your book. I'll try to pick some that are not in there, or some of the ones that are more interesting and useful to do relative to the homework, which, by the way, is now online, as are the next several homeworks beyond it. But I figure we'll wrap up, instead of running over, with enough time to answer questions if anyone has them, since there are a few people in the chat. Any questions? that anyone wants to ask before the end of class for those who are attending live? I'm checking the email. I don't see any other questions sitting in there. Okay. Well, if you're typing, please feel free to continue typing. I won't end it right away. But yeah. So if you're starting to feel at all overwhelmed, though, please let me know as you're watching these videos. I know that this section right here suddenly starts to feel like a lot, and that like I'm probably not covering this in a lot of depth for any of it. And this is kind of necessarily how it's got to be if we want to get into any of the more interesting material and not spend a inordinate amount of time just redefining familiar functions for a slightly larger set of numbers. My goal here is to just basically spit these definitions at you and highlight the general process of how we go about it. None of the calculations in this section are difficult, so I don't think that there's a high likelihood of you encountering trouble as you read through it. I just really recommend that you actually do go through and read through section 1.3, because having a poor understanding of the elementary functions will make your life much more difficult in this class. So just go through, look at it, make sure you kind of get the idea, and let me know if you have any questions. I'm here to help. Okay, I'm not seeing any questions in the chat. We are at the 50-minute mark, so we'll call it quits for today. We'll do an example or two at the start of class next time. Then we'll continue on to talk about something else. After elementary functions, we're going to get into something fun and interesting and much more important for the world of more advanced mathematics. A familiar topic, continuity. Everyone knows about continuity from all of our other calculus classes and things like that. We talk about it in Calc 1. I think we maybe even talk about it in Algebra Trig at UYO. But we talk about it at a certain kind of low level, and relative to real valued functions. We don't make any reference to topology, and we'll begin to correct this deficiency. And while we won't go into the full formalism, this isn't a topology class, we will begin to hint at a little bit more of the mechanics behind what makes continuity such an important and interesting property, and why we care about it, since continuity will play a central role in many of the proofs for the remainder of the class. So we'll kind of get the last bit of the introductory stuff out of the way with continuity, and then we'll begin to get into a lot more of the interesting and genuine story of complex analysis type things, not just defining elementary functions or talking about continuity and things that you've probably heard about before. The continuity section, like this one, is quite long. I should mention. It is a lot of different stuff thrown at you very quickly, so we'll go through it relatively fast. And then finally, we'll get to analytic functions. This will be the beginning of the grand story of holomorphy and the many nice equivalent properties to holomorphy or complex differentiability. And it will begin our journey towards the eventual realization, and it's underwhelming when you say it out loud, that there just aren't that many holomorphic functions. In fact, there are so few of them that there are lots of ways to get them without specifying what they actually are, and this will occasionally allow you to access otherwise difficult to know about information, and that is the story that we will tell. But I think we'll call it for today since I'm rambling and I can hear my son crying upstairs. So I better run in there and see what's going on. All right. Cool. Have a great night.